Welcome to Maths with EJD. In this video, still talking about probability, we focus on expected value and variance of random variables. Okay, so let's start by digging into the meaning of expected value. Okay, the expected value, which is also known as the mean, expected value or mean of a random variable provides a measure of the central tendency of its probability distribution. So it's more like you have a probability distribution, but you need a single value to estimate the whole distribution. That is why we talk about central tendency. So of its probability distribution. Okay. So it represents the average outcome if an experiment is repeated, many times. Okay, so that's the basic idea behind expected value. So when we talk about expected value in connection with random variables, right? So let me switch here. Let's say that the expected value, which is denoted by E of the variable X, the random variable X, is calculated using this. Okay, let me put it this way. I think we need to clearly make repeated many times. Okay, so now what I meant to say here is that for a discrete random variable, we've been talking with, I did a video on discrete random variable and then later on continuous random variable. So when we talk about expected value, there's the way we approach it for both variables. So for a discrete random variable, the expected value E of X is calculated using expected value of X equals summation over X, right? Then that's X, the variable X itself, multiplied by the probability that X is equal to X. Of course, you can rewrite this as something like this, summation over X, right? Of X times P of X. So that means that this now is the same as this. So here now, X are the possible values, of the random variable, So small x is the specific value the random variable the random variable big X can take. So where X are the possible values of random variable X, and P of X equals X. P of X equals X is the probability of X taking the value X, like that. So the key thing here is to pay attention to this. So the expected value of X is the summation of the product of the variable, the specific value X, and the probability that the random variable takes that value actually. Okay, so we'll have some examples following that. All right. Okay, let me go for the examples right now. So let's take the example. Consider a fair die rule, I made a whole video talking about probability with coins and dice, so you can get deeper understanding of the idea of fair die and all that there. So consider a fair die rule, right? So let X be the outcome of the rule. Be the outcome of the rule. The possible values are 1, 2, 3, 4, 5, and 6. So each with probability, I mean, this is well known, each with probability of 1/6. So you have equal chance of getting 1, 2, 3, 4, 5, 6. So that means 1/6 for a fair die, that is, a die that has not been manipulated. So to find, okay, to find the expected value, so expected value of x now is summation from x equals 1 to 6, because you have 6 possible values of x. So 6, so that's x dot 1/6. And you know, that's more like saying when x is 1, so you have 1/6. You know, you can rewrite this as summation from x equals 1 to 6 of 1/6 times x. That's cool. So and then this is a summation now. So it means we can have 1/6 when x is 1, 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. So it's simply more like you have 1/6 into 1 plus 2 plus 3 plus 4 plus 5 plus 6. So that's 1/6 times, if you to add from 1 to 6, you just have 6 times 7. That's 42 divided by 2. That's 21. So that's simply you having 21. Okay, I can continue straight there. So I have 21/6. 3 goes up there, that's 7. 3 goes down there, that's 2, and that's 3.5. So the expected value when you roll a die, so the average value of outcomes you can ever get is 3.5. That's what that is about. So you can say that, so the expected value of rolling a fair die, is actually 3.5. That's the expected value when you roll a fair die. Okay. So that goes for discrete random variable. Now, we are still talking about expected value. So, but that's for discrete random variable. What if we talk about expected value for continuous random variable? Let's talk about that. So for continuous random variable, for continuous random variables, the expected value is given by same notation, expected value of x, but now we are dealing with continuous random variable. So, and that's summation. We use that's integral, rather. We use summation for discrete and we use summation for continuous. So minus infinity to infinity of the possible value that the random variable x can take, multiplied by the value f of x, the probability density function, which we talked about in a previous video. So you have this, right? Where f of x, like I said, is the probability density function. Probability density function. That is PDF of the random variable x. So now the focus is on this. I meant to use a different one. So now the focus is on this for continuous random variables. And of course, this x is a value the random variable can take, and f of x is its PDF, its probability density function. Okay, now that that is well taken, can we then move on to take an example that drives the point home? So let's say that, let's say, suppose X follows a uniform distribution. X follows a uniform distribution between 0 and 1, between 0 and 1. Okay. So the PDF, the probability density function, is f of x. Okay. It's okay. I mean, usually the uniform distribution like that will be in form of a step function. So you have the PDF is f of x. Okay, good. We can just do it this way. So the PDF is simply f of x equals 1 for x lying between 0 and 1. So 0 is less than or equal to x is less than or equal to 1. So the expected value is, it's uniform distribution, right? That's why the value is constant there. So the expected value is simply this: expected value of x equals integral from 0 to 1. We're talking about from 0 to 1 of the possible values of x, which is x multiplied by f of x itself. F of x is actually 1, okay, dx. That's what we have to deal with. So in all, we're saying integral from 0 to 1 of x dx, and then we can integrate x. If you integrate x, you get x squared all over 2 from 0 to 1 now. So that means you have, for easy handling, you can take out the half, so you have x squared from 0 to 1. So don't forget, this is still talking about the expected value of x, and that is equal to 1 over 2 into, when you put 1, that's 1 squared, minus when you put 0, that's 0 squared. So that's 1 over 2 into 1 minus 0. And then that is 1 over 2 into 1. So half the value is half. The expected value for a uniform distribution between 0 and 1 is actually half. I mean, it's more like taking the average. 0 plus 1, 1 divided by 2, that's 1 over 2. So, I mean, it's that kind of thing. That what is the central idea you can get when you find the expected value of something like that? So all you need to just know, once you have the PDF, then you're good to go. Just have the PDF of any distribution you're working with, and then you just know integral x times that PDF dx, and that goes. All right. So let's move on to talk about variance. Let's talk about variance. Okay. Well, I let me just make this final statement. I've said it already. I just want to write it down. So the expected value of a uniformly distributed random variable between 0 and 1 is 1 over 2. That's all. Okay, so that is about expected value. So we've done expected value for both discrete and continuous random variables. Now let's move on as we talk about variance. Okay, so for variance now, it is to be known that variance measures the spread. The expected value measures a specific value, a central tendency, you know. But then variance talks about how it spreads to the right and to the left. So some kind of range. So this guy is in the center, and then you have variance going to the left and to the right like that. So variance measures the spread or dispersion. Expected value is central tendency, but this one is dispersion. It's a measure of dispersion. So variance measures the spread or dispersion, how removed from the central tendency the distribution can be. So variance measures the spread or dispersion of a set of values, It quantifies, it quantifies how much the values of a random variable differ from the expected value. Okay, so you have the expected value somewhere in the center, and then variance tells you how a set of values are removed from that central tendency. So let's talk about discrete variables now. So for discrete random variables, the variance VAR of X is calculated using var X equals, now the variance of X is actually the expected value of how removed X is from the actual expected value of X, that squared. So the square of the departure of each value of X from the expected value. So we take the square of that, and that tells us about the variance. Now, if you look at this, you will see that this now is more like, how the whole expected value thing goes. So this will just now be from the definition of expected value. You remember expected value for discrete variable. Okay, I guess I need to use a different marker to bring that to our remembrance. So expected value of X is actually summation from all over X of X itself multiplied by the probability that X is equal to X, or a small p of X like that. So in this case now, we're talking about expected value. Now, so it means whatever we have here, this is more or less like our X in this case. So that is why if we break that down, so it means we have summation over X of that. That is, so in this case, now we now have X minus expected value of X all squared multiplied by the probability that X is actually equal to X. So we can break it down that way. Alternatively, we can then have the variance of X, trying to see how to drive the point home. Okay, well, that's one way to look at it, right? That's one way to look at it. But I also want to see I want a logical way to arrive at the final definition. So that's correct, right? But if you have variance of X, right, it's actually the expectation. It is the expectation of X minus the expectation of X all squared, like this. So, one thing we can do is, this is like the expectation of, when you expand this, it's more like you have X minus expectation of X into X minus expectation of X. Okay, so that is like you have expectation of X times X squared, then minus X times expectation of X. Okay, and then the next one again, you have minus X times X, that's minus X again times expectation of X plus the expectation of X all squared, something like this. So that's expectation of x squared minus 2x expectation of x plus expectation of x all squared. Okay, so next we have this that so this is expectation. This is expectation of x squared, if you operate it like that. So expectation of x squared minus expectation of 2x expectation of x. Then you have expectation of x all squared. Now, we need this logic here carefully. We are still talking about variance of x, don't forget. So expectation of x squared, of course, that is something we can deal with. So expectation of x squared is something we can find. But I think the issue comes when we have all these other expectation of something. So here now, you have so this is like okay, the expectation of x is going to it's going to, let me see, trying to see this. Okay. Or could we have done something at this level? Expectation of this. So we have expectation of x squared. And at this point, right, we have 2 times the expectation of x multiplied by the expectation of x. Okay. Then plus the expectation. Okay, this is already done, right? So plus the expectation of x squared. So normally, right, this is as good as saying that we have expectation of x squared, because this expectation just is there. Okay, trying to find a very nice way of landing to the destination. Okay, so let me see for this part now. Okay, well, when we resolve all this, right, there should be some logic I need to explain around all this. But at the end of the day, what we just need to know is that, of course, this is expectation of x all squared, right? So at the end of the day, when it's all done, we have variance of x is expectation of x squared minus expectation of x, like this, all squared. That is variance of x. So probably in a future video, I'm going to do like a fast math solution to clarify this. So right now, I'm not getting the logic. I should really explain here. Okay. So, but at the end of the day, this is really key. The variance of x is actually the expectation of x squared, all right, minus the expectation of x all squared. So that goes. Of course, expectation of x squared is actually the expected value of x squared. And we know how all of that can go. Maybe I can still trace something here. So x minus this. And then that comes to this point. This is p of x. Okay. So this times the probability of that x happening. Okay, I mean, for now, let's hold on to this reality that the variance of x ends here. Okay. So with this now, we should know that variance of x is simply expectation of x squared minus expectation of x all squared. So that's settled. So that is going to guide whatever we have to do in the future. If we need to calculate something, if we need to calculate the variance of x. So if we need to take an example, we can look at the initial one we took for the what is it now? That's The fair die, yeah. The fair, or is it a fair? Yeah, the fair die thing. Okay. So if we use that fair die example, we can still do the variance in this case. So using, I guess I want to change. Okay, I want to go green now. Using the fair die example, we first find the expectation of x squared, right? So, I mean, isn't the fair die example, right? Let me just go straight. So we have that the variance of x already is expectation of x squared minus expectation of x all squared. That's variance. So in that case, that time, you remember that the expectation of x squared would simply be summation from x equals 1 to 6 of x squared multiplied by the probability that big X is equal to small x. Okay. So in that case, and probability that big X is equal to small x is simply 1/6. So that's summation from x equals 1 to 6 of x squared multiplied by 1/6. So that's like, you can even bring out the 1/6. So you have 1/6 summation from x equals 1 to 6 of x squared. And that's all we have. So that means you have 1/6 into each one. So you have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. That's all that is about. And that's simply, so that would be 91/6. Because this is, okay, let me go step by step. So it's 1 plus 4 plus 9 plus 16 plus 25 plus 36. So this is 71. This is 87 plus 9. 87 plus 9 is 96. 96 plus 4 is, oh, what am I saying? 25 plus 36 is 61. Sorry, 61. 61 plus 16 is 77. 77 plus 9 is 86. 86 plus 4 is 80. No, 25 plus 36, 71. 71 plus 16. 71 plus 16, 87. 87 plus 9. 87 plus 9 is 25 plus 36, 61. Yeah, 61, sorry. 61 plus 16, 77. Yeah, 77 plus 9, 86. 86 plus 4, 90. Yeah, 90 plus 1 is 91. Okay, so that's 91/6. Sorry, that was a bit of something. So this is the expected value of x squared. That's 91/6. All right. So we have that. Then the next thing we need is expectation of x all squared. Expectation of x all squared. That will simply be the expectation of x we got the other time already, That's do we have to go over that? We got the expectation of x up here already for a fair die. So we can just lift that and bring it down there. So this is the process, and we got 7/2 the other time, or we can say 21/6. So we can just lift the 21/6. So it's 21/6. So I can just even leave this as expectation of x. That's 21/6. So that the variance of x is expectation of x squared minus expectation of x all squared. So that is 91/6 minus 21/6, 21/6 all squared. So if you tidy that up, that's like 91/6 minus 21 squared is 441 divided by 36. And then the LCM, so if you do all that, of course, this is 36 now. So 6 here. So this is 6 times 1, 6. That's 546 minus 441. 546 minus 441. So that's 105, I believe. 105 over 36. So 105. So we're dealing with variance of x, don't forget. 105 over 36. So 7. Oh, is it 7 that goes? No, not 7. 4. 3 goes. 3 goes in 105. That is 35. That's 3 in 10 is 3. 3 in 15, 5. Then 3 in 36 is 12. And that is approximately 2.92 or so. So that's approximately 2.92. Okay. So that's how to go about the variance. Expected value of x squared minus expected value of x all squared. Okay. So we have that. Now, let's talk about, this is for discrete variable now. Let's talk about continuous random variable. How do we calculate that? So it's still basically the same expression, except that now we are dealing with integrals, right? So we say that for continuous random variables, for continuous random variables, for continuous random variables, so the variance, the variance is given by variance of x, which is equal to summation from minus infinity to infinity of x minus expectation of x all squared multiplied by the probability density function d of x. So it also evaluates to the same thing, variance of x equals summation of, expected value of x squared minus expected value of x all squared. So in this case, now if you want to do the same thing we did with the continuous random variable the other time, so we can say that for, I guess I want to switch. Okay, let me switch to this. So for x uniformly distributed like before, for x uniformly distributed between 0 and 1, the expected value ex is 1 over 2, if you remember. That was what we got the other time. The expected value e of x is actually 1 over 2. So from there we can find the expected value of x squared, which will simply be integral from 0 to 1 of x squared times f of x dx. And we know that f of x for this kind of thing, f of x for that is 1, like we had the other time. So that means integral from 0 to 1 of x squared times 1 dx. That is integral of x squared dx from 0 to 1. Still talking about expected value of x squared now. So that is integral of x squared is actually x cubed over 2 over 3. Okay, x cubed over 3 from 0 to 1. And for easy handling, like I say, you can bring 1 over 3 out. So you have x cubed from 0 to 1. So that is 1 over 3 into what, put 1, that's 1 cube minus put 0, 0 cube. So we have 1 over 3 into 1 minus 0. Okay, 1 over 3 into 1 minus 0. And that means you have the expected value of x squared is actually 1 over 3. So that helps. So we can now go ahead to look for the variance. So again, we remember variance of x is expected value of x squared minus expected value of x all squared. So expected value of x squared now is 1 over 3 minus expected value of x 1 over 2 squared, like that. So that means we have 1 over 3 minus 1 over 4. 1 squared is 1, 2 squared is 4. LCM now is 12. So 3 in 12 is 4, minus 4 in 12 is 1 times 3 in 12 is 4, minus 4 in 12, that's 3. So we have 1 over 12. And that is approximately 0.0833. So that's the idea here. All right. So we see that the expected value represents the long-term average, while variance represents how much the value spread around the expected value. Okay, so if you want to, okay, let me just talk about this interpretation here before we draw a curtain on this. Say that you have, okay, let's interpretation. Okay, so talking about expected value now. So talking about expected value. Okay, so this represents the long-term value, the long-term average value, the long-term average value. So for the die, 3.5 means if you roll the die many times, the average outcome will approach 3.5. Okay. Then for a uniform random variable, between 0 and 1, the average outcome will be half, which is more like 0 plus 1 divided by 2. Then talking about variance now. Of course, variance represents spread, like I said. Variance, this represents how much the values spread, around the expected value, Okay, so for the die, which we saw before, for the die, a variance of 35 over 12, which is approximately 2.92, indicates the outcomes are somewhat dispersed. The outcomes are somewhat dispersed around the mean. And then for the uniform distribution, for the uniform random variable, a variance of 1 over 12, which is approximately 0.0833, shows less spread around the mean. It shows less spread around the mean compared to the die rule. Okay, so you see this is the bigger spread. 2.92 is a bigger spread than 0.0833. So we've come to the end of this video. So if you have not subscribed, be sure to do that. And of course, hit the notification bell so you can always get alerted when a new video is released. And don't forget to comment, like, and share. See you next time. Bye.